In this section, we're going to introduce logarithms and look at their properties. So what a logarithm is, it's another way to write an exponential equation. If we look at this a to the y equal to x, that is an exponential equation where we have our y as the exponent. And for every exponent, there has to be a base, and that would be our a. So for our log equations, the base is going to be positive and not equal to 1. And the reason why we have those conditions is because it's not just a log equation, it's a log function. So to make sure that it is a function, the base has to be positive, but also to make sure it's a one-to-one function, the base is not going to be equal to 1. So anyway, what we can do is we can rewrite this exponential equation, and we call this the exponential form of an equation. So this is the exponential form. And why would I want to rewrite it? Well, notice that the exponent y, if I wanted to figure out what that is and get y by itself on one side of the equal sign, there is actually nothing algebraically that I could do to get the y by itself. We don't have anything algebraically that will isolate that y. So a few hundred years ago, a mathematician named a new function called the log function. And what the log function allows us to do is take that exponent and get it by itself on one side of the equal sign. So we're solving for the exponent. The base is still going to be the same. So we got the exponent by itself, and it's now equal to this new function called log. And we read this as log base a of x. And here we call x the argument for the function. This is logarithm form, but I'm going to shorten it to log form. And we can go back and forth between the exponential form and the log form, depending on what we need to do with these equations or functions. We're going to explore the function part of our logarithms in later sections, but I thought it'd be nice to bring it up now so you can see the relationship between these two forms. First of all, y equal to log base a of x. If I were to replace y with the function notation, in this case it would be f of x. Then I have this function log base a of the argument is x. So you can look at this log base a as being f. So it's like f of x. And that's important because you cannot divide by the x and get rid of it. It's all one piece. It's log base a of x, like f of x. It's not a multiplication. It's not log times x. So since it's all one piece, the only way we can break it up is by using log properties. But what I'd like to do now is go back to that exponential form. So remember, this was a to the y equal to x, and it is a function. And not only is it a function, it's a one-to-one function, which means if I were to exchange the x and the y to write a to the x equal to y, then that would be its inverse. If I were to reorder this as y equal to a to the x, you may recognize this as what we talked about in our last section, which was our exponential functions. And that's the relationship between the log and the exponential functions. They're actually inverses of each other. So log functions are going to be inverses of exponential function going to be inverse of a log function. First thing we're going to do is we're going to translate between the exponential form and the log form. In example 1a, we want to take 3 to the y equal to x and write it in log form. So remember, we're trying to isolate the exponent. In this case, the exponent is y. Oops. Why do I do that? It's going to be equal to log. Now the base is 3. That remains the base, so it goes below the log. And then the argument is the x. So we're just rearranging that exponential form and then adding in that log notation. Let's try that again in part B. So again, the idea is to isolate the exponent. And here you don't want to get hung up on the variable a, y, x. You want to look at the form itself. The form says whatever this exponent is, and in this case I called it m, I want to get it by itself on one side of the equal sign, and then write log of whatever the base is. Here the base is 1/5, so that goes below, and it's equal to the argument for log would be the 125. So notice that we're not taking 125 and dividing it by 1/5 or multiplying it by 1/5. Those are all separate pieces. They cannot be combined at all. And that'll come up again. But let's go the other way. Let's say that we have an equation in log form and we want to translate it back to exponential form. And we do this often when we're going to graph log functions, which we'll do in a later section. Or sometimes it helps us to solve log equations. So for example, if I had in part A log base 5 of 125 is equal to x, well, it's kind of hard for me to see what that x value is. But if I translate this back to exponential form, the base is 5 and the exponent is x. So this is going to be base 5 exponent x equal to 125. And you could probably see that x has to be 3. But if you don't, recall what we did in the prior section, we got the bases to match. So I can write 125 as 5 to the third power. And now that my bases match, gone, and I get x is equal to 3. Let's try this again in part B. We have log base x of 81 is equal to 4. So this time I'm trying to solve for the base x. Again, rewrite it. The exponent is 4 and the base is x. So this is going to be x to the 4th is equal to 81. Again, you could probably guess that x has to be 3. But normally what we would do when we have x to the 4th or squared or to the 3rd is we would take the root of whatever the exponent is, and what we do to one side we have to do to the other. Typically when you have an even root you would add the plus minus, but remember our base is positive, so we don't use the negative here. We just keep it as the positive whenever you're solving for the base. The 4th root and the exponent 4 cancel, so I get x equal to the 4th root of 81 is 3. And we'll do a few more. Part C, I have log base square root 3 of x is equal to 4. This time I'm solving for the argument x. Rewrite it as base would be the square root of 3. The exponent is 4, and that's equal to x. So the square root of 3 to the 4th power is 9. And I'm done. X is equal to 9. Last one. Well, this looks crazy. I want to solve for the argument x. The base is 1.2345. The exponent is 0. Well, that's easy. Anything to the 0 power is 1. So it looked weird, but it actually came out really nice. What we're going to do now is we're going to talk about some more properties with our log functions. But first, I'd like to talk about two bases that we use very often. In fact, we use them so often that we've simplified the notation. The first one would be what we call our common logarithm. And it's a common logarithm because we commonly use it since our numbers have 10 digits. That's how we count. We count in base 10. So base 10 is our counting numbers. We use it so often that we'll just write log of x and we'll leave off the base. So if you see log without a base written, you can assume that it's base 10. The other log would be our natural logarithm. And going back to our prior section where we looked at e, which is about 2.72, that would be the base here. So log base e is used so often because often things, remember, they grow or decay at base e, that we replace log of e with ln. So just to be clear, log of e is ln. The x does not change. And why is it ln when it's natural log? Why isn't it nl? And that's because the mathematician hundreds of years ago that actually named these functions was French. So it was actually logarithm naturel. So in French, it is ln. Regardless, if you see ln, that's just log base e. Now these are used so often that all scientific calculators should be able to compute base 10 and base e. Now in this following table are a ton of properties. So don't forget for the final to write some of these guys down. So let's say that we have all of these conditions. Did we have some base a that's not equal to 1, and it's positive. And let's just look at positive x and y values. And then we'll look at real numbers. So these could be negative and 0, k and r. So they're just going to be any real numbers. We'll look at this first property that says the log base a, so a is just any base, of 1 is equal to 0. So it doesn't matter what your base is. If the argument is 1, the log is equal to 0. And I can verify this by just switching this to its exponential form. So remember, it's base a. The 0 is the exponent. So is it true that any positive number to the 0 power is equal to 1? Yeah. And then there's a corresponding property with the natural log. Natural log of 1 is also equal to 0. Again, if I were to verify that, remember that the natural log is simply log base e of 1 equal to 0. Switching that to the exponential form, the base is e, the exponent is 0, e to the 0, yeah, that's equal to 1. And all of these properties pretty much can be verified by, in some form, using the exponential form. We'll go to the next property, which says that if the base and the argument match, it's going to be equal to 1. We'll go ahead and verify that very quickly. Base is a, exponent is 1. Is a to the 1 equal to a? Obviously, it is. And then we have that corresponding property with the natural log. So natural log is log base e, so natural log of e is also equal to 1. And now 3 says that if the base and the argument are the same, and let's say the argument is raised to some exponent k, well, it says that base arguments same, they cancel, and you're left with just the exponent. 4 is interesting. We don't use this one very much, but it says if you take some base a and its exponent is log base a of some k value, then those cancel and you just get your k value. 5, 6, 7, we use those very often. Now remember, logs are exponents, so they follow the operation of exponents. In an exponent, whenever you multiply with the same base, remember what you do is you add the exponents, which is why we're adding the logs, because those are exponents. So log base A of a multiplication, A again is any base, can be split up into log base A of x plus log base A of y. And this is an equal sign. So oftentimes we will expand it out because it's easier to simplify if it's expanded out. But sometimes we'll actually bring it all back into one log to solve. Something to note on all of these properties, notice that in front of the log, there's no number. It's not like 2 times the log of blah, blah. These properties can only be used if the log has coefficient 1 in front of it. So if it was 2 times the log of A, couldn't use these properties. You'd have to get rid of that 2 first. Property 6 says that if you have some base and you're dividing, then it's going to be top minus bottom, which makes sense. Think of when you have same base and you're dividing same base, you would take the top exponent minus the bottom exponent. So it's the same idea here. And then our last property is log base A of x. Let's say that your argument x was raised to some exponent. Well, what you can do is you can bring that exponent out into the front of the log, and this reads as r times, so it's multiplication, times log base A of x. So if you did have a number in front of the log and you wanted to use those other properties, you could bring that r back up, because remember, this is an equal sign. These properties work both ways. You could bring that r back up as the exponent on x, and then you can use all those other properties. And don't forget that we also have the corresponding properties for natural log here as well. We're going to go back to solving just a couple of real simple equations, but we're going to use the properties instead of switching it to the exponential form. And then the rest of this section, we're going to be working on expanding and contracting our logs using the property. We're going to solve more complicated log equations in later sections. So example 3, we're supposed to solve. Now I could switch it to exponential form. However, I noticed that 81 is 3 to the 4th power, I believe. So if I were to rewrite this as log base 3 of 3 to the 4th equal to x, maybe I could simply use one of those properties. And it looks like that would be going back up. That would be property number 2. 3 would be like the A value. Oops, no, that's not property number 2. Erase. That would be property number 3. 3 is going to be the A, and 4 is the K, and X is the K. So if you have the base and the argument matching, remember that they cancel, and that would be by property number 3. These guys would cancel, and what you're left with is 4 equal to x. So again, that's using the properties instead of switching it to exponential form. But we could switch it to exponential form. We could just as easily say, okay, this is base 3. Just as a reminder, the exponent is x. That has to equal to the argument, which is 81. And then getting the bases to match, we get down to x is equal to 4. Let's look at B. B says log base x of 5 squared is equal to 2. So I could write 25 instead of 5 squared, but I don't want to do that. I'm going to use property 7, And I'm going to take this exponent and bring it out into the front to write 2 times log base x of 5 equal to 2. And that was by property 7. And then I'm going to divide both sides of this equation by 2. Because we brought the 2 in front, it's 2 times all of this. I'll put this in parentheses just to emphasize that log base x of 5 is one piece, so it's whatever this is times 2. So I am allowed to divide both sides of the equation by 2. On the left, the 2 will cancel, and I'm left with log base x of 5 equal to 1. And now when you go all the way back up and you look at property number 2, it says whenever a log is equal to 1, it must be that the base and the argument match. So the only way a log can equal 1 is if the base and the argument are the same, which tells me x has to be equal to 5. Again, that's by property 2. So that's just using the properties instead of switching it to exponential form, but you can always just switch it to exponential form if you're more comfortable with that. The next thing we're going to do is we're going to practice using the properties to stretch things out and bring them back together again. In example 4, it says use properties of logarithms to expand the expression completely. In part A, this is log base 3 of 2 over 7. And I know by property number 6 that I can rewrite this as log base 3 of 2 minus log base 3 of 7. Again, that was by property number 6. I can't expand that anymore, so I am done. Let's move on to B. Log base 5 of 5 times n divided by p. I see that division. So again, I'm going to use property number 6 to write this as log base 5 of, the top part is 5n. Division means minus log base 5 of p. However, notice in this first expression, I have a multiplication. I have 5 times n. So I can use property 5. So the first thing I did was I used 6. Now I can use property 5 to rewrite that multiplication as log, oops, I want blue, as log, and now that looks too ugly, it's going to irritate me. Log base 5 of 5 plus, because it's multiplication, log base 5 of n, and then I still have the minus log base 5 of p. This is expanded as much as I can. However, I notice I have a log base 5 of 5 where the base and the argument match. So if we look at property number 2, that's equal to 1. So not only could I expand it, I can use the property to simplify this further. And I think that's as far as I can go. That is expanded out. We will keep going with more examples of expanding. Here, notice that this log doesn't have a base, so I'm assuming it's base 10. We'll go ahead and expand this out. I have the division. So again, I start with property number 6, where I take log. It's base 10. I'm not going to write it. I'm just going to write log of square root of x, and then it's going to be minus log of y z. And now I don't want square root of x, I just want x. So remember that this is log of x to the 1/2. So whenever you see a root, you can replace it with its rational exponent. And then we're going to use property 7 to expand that out further by bringing that 1/2 out in front. Also notice that I have multiplication here. It's y times z. But be careful because this is log of y times z. This is one piece. So if I expand it further with addition, I have to distribute that negative on the outside. So this is log of y plus log of z. By property 7, I'm going to bring that 1/2 out in front, 1/2 log x, and then I'm going to also distribute the negative, so I get log y minus log of z. So this would be completely expanded. This is also a nice time to look at a shortcut whenever you're using property 6 when you have a division and you also have maybe multiplication. Is anything in the top is a positive, anything in the bottom is a negative. So I didn't actually have to do this second step where I put parentheses and I expanded the yz out further. I could have gone straight to, I see y times z, but they're both in the bottom, so they would both be negative. So again, if it's in the top, it's a plus. If it's in the bottom, it's negative. And now in D, I could use the last property, number 7, to take the exponent 3 out into the front of the natural log. And in parentheses, I have x plus 5. And stop. You cannot go any further. This cannot be expanded. So a common mistake is to write this as natural log of x plus natural log of 5. You cannot do that because remember that parentheses around the x plus 5 means that that is the argument on the natural log function. It's not natural log times x plus 5. It's natural log of x plus 5. And we have no property that looks at an argument with either addition or subtraction and breaking that up. So this is actually as expanded as it's going to be. Now that we've expanded things out, we're going to try bringing them together. In example 5, we're going to use the properties of logarithms and write as one log. So bring them all together if possible. It may not be possible though. First thing I want to make sure is that the number in front of the log is 1. Notice that this is log base 3 of x in part A minus 3 times log base 3 of y minus 1/2 log base 3 of y. We got to get rid of those numbers before we could use the properties to bring these together. So we're going to use property number 7 to take the number in front and bring it up as the exponent on the argument. If I were to rewrite this, it would be log base 3 of x, can't really do anything with that, minus log base 3 of y to the third minus log base 3 of y to the 1/2. Now I can use all the properties. I just have to make sure that all the bases are the same. So notice I have log base 3, log base 3, log base 3. I can combine it into one log base 3. And since this is a plus, even though we don't write it, minus minus, that tells me I'm going to have a fraction. The x will go on the top because that's a plus log 3x. But since I have a minus here in front of the log base 3 of y to the third, that means y to the third goes below. Again, I have a minus in front of the log base 3 of y to the 1/2. So the y to the 1/2 goes below. Negatives below, positive above. And now this is 1 log, but notice I have y to the third, y to the 1/2 in the denominator. I can combine those by just adding the exponents. So 3 plus 1/2 would be 7/2. And this would be log base 3 of x over y to the 7 over 2. And I think that's as far as I can go. Not necessary to write that with radicals. Let's do this again with part B. So notice we have the 2 in front of the natural log of a, and I think that's it. So I'm going to bring that 2 up and rewrite this as natural log of a squared minus natural log of a plus b plus natural log of a minus b. Same base, natural log, natural log, natural log. I can bring it all into one natural log where the pluses go on top. So I have, this is a plus, the a squared, and this is a plus, the a minus b. So it's going to be a squared parenthesis a minus b. I didn't make this long enough. And the only minus I have is that a plus b. When these arguments start getting really big like this, oftentimes we'll put another set of parentheses or maybe a bracket around it to indicate that this is all one piece. And this is actually done. There's nothing I can do to simplify. Maybe if you want, you could distribute the a squared and get rid of the parentheses on the top. But I'm going to leave it that way because nothing cancels. All right, part C. I have a 2 that I need to get rid of in front of the first log. I have a half, and I also have a 7. So I'm going to rewrite this as log base 3 of x squared plus log base 3 of x to the 1/2 minus log base 3 of y to the 7. Log base 3, log base 3, log base 3. I can combine it into 1 log base 3 of the x squared goes on top, and so does the x to the 1/2. But it's a minus log base 3 of y to the 7, so the y to the 7 goes below. And now in the numerator, the x squared, the x to the 1/2, I can combine them by adding 2 plus 1/2, which should give me 5/2 to get log base 3 of x to the 5/2 over y to the 7. And I believe that's as far as I can go. All right, last one of these types of problems. Let's see, I have that 3 and the 1/2. So we'll rewrite as log base 3 of m minus log base 3 of n to the third minus log, this is base 5 of 4 to the 1/2. So these first two can be combined because they have the same base, but the last cannot. So let's just go ahead and combine log base 3. It's a subtraction, so it's going to be m over n to the third, and then minus. Although I can't combine because this is a different base, it's base 5, I can rewrite that 4 to the 1/2. Remember, that is the square root of 4. So I can replace 4 to the 1/2 with 2. And that's it. I can't go any further there. So it was not possible to write this as 1 log. So we talked about the base 10 and the base e being in your calculator. Now, if you have a fancy calculator that does other bases for logs, that's great. but most people don't. So it may be helpful to change your base. The change of base formula is fairly simple. It says if you have any log with any base, you can always rewrite it with whatever base you choose. So it would be log base b over log base b. And the argument goes to the top. Oh, I don't want that. And the base goes to the bottom. I often like to use natural log because it's less writing. So argument up top, base on the bottom. In example 6, we'll go ahead and use this change of base and then a calculator to approximate the expression log base 3 of 11. So my calculator doesn't do log base 3. In order for me to figure out what log base 3 is, I would have to rewrite this. So I'm going to do it with base 10. So that's log, I'm not going to write base 10. I'm just going to write log of the 11 is on the top and the base 3 is on the bottom. And we'll see what that is. In a calculator, we'll get an approximation. Or maybe I can do log base 3 of 11 and write that as natural log of 11 over natural log of 3. Now, when I put this in my calculator, why don't we round it to 4 decimal places? I get approximately 2.18265, so 27. When I do natural log of 11 over natural log of 3, I get the exact same thing, which is exactly what I was supposed to get. And the only reason why I did this in 2 different ways is so that you could see that it really doesn't matter which base you choose, as long as argument's on top, base goes on bottom. Now, a common application that we do for logs is with pH. So I know everybody's heard of pH this, pH that. Well, the pH scale goes from 0 to 14, where in the middle here, the neutral, that would be 7, which makes sense because it's directly in the middle. Something that's neutral is uncontaminated water. I am specific about that because oftentimes if water does have contaminants in it, it could throw off the pH of the water and it usually goes alkaline. Blood and urine are similar to water. They're close to neutral. Oftentimes when you get lab tests done, they'll have you do a urine sample, especially if you have an infection, because that may throw off the pH and it may show up in your urine. Let's see, battery acid, that would be acidic. That's way at the end here, near the 0 ones. And then alkaline, often we say it's basic instead of using the word alkaline. Bleach is at the upper end here. So when we try to figure out what pH is, so that's just some number from 0 to 14, we're going to use a log formula. So pH is equal to negative log of this odd expression. So this H sub 3 O plus, that's expression is hydronium ion concentration. And the measurement is in moles per liter. So if you have taken chemistry, you may be familiar with this. And the hydronium ion concentration is just going to be some number. So this is going to be a good time for us to review how to write in scientific notation. Now, normally when we give a pH number, it's to the 10th, so to 1 decimal place. In example 7, it says find the pH of a solution where the hydronium ion concentration is equal to 1.8 times 10 to the negative 4. And then we want to know, is the solution acidic or alkaline? All we have to do is use the formula. So, oops, Y. So our pH, Y, I want blue. Oh man, this is terrible. Oh well, that's not going to work. So our pH, so sad, is going to be equal to negative log of whatever this hydronium ion concentration is. In our case, it's going to be 1.8 times 10 to the negative 4. So you would simply just plug this into a calculator. And when I plug it into my calculator, I am going to round to one decimal place, so I get 3.7. And it's an approximation because I've rounded it. If you choose, you could do some simplifying. So notice that I still have this negative in front, but it's multiplication on the inside. So this would be the same as log of 1.8 plus log of 10 to the negative 4. And then, although we don't write it, remember this is base 10. So in this last expression, this is log base 10 of 10 to the negative 4, and we can use one of our properties that says this cancels, and it's just the negative 4 or minus 4, which means this would be equal to negative log of 1.8 minus 4. Now that minus 4 is not part of the argument for the log. The log is log base 10 of 1.8. The minus 4 is separate. And then if we were to distribute that negative, we would get a negative log of 1.8. And then the plus 4 would be separate. So if you were going to put this in the calculator, this is one piece. And you should get the same value. So you can do some simplifying if you choose to, or just put it straight into the calculator. Now let's say that we actually have the pH and we want to go the other way. We want to figure out what our hydronium ion concentration is. Well, again, we have the pH. In this case, it's 8.8. So we know it's going to be equal to negative log of what we need to find, the hydronium ion concentration. So in this case, I would first get rid of the negative in front of the log by multiplying both sides of the equation by the negative to get negative 8.8. And the reason why I want to do that is, remember, we want to get the log by itself. In this case, I would go ahead and change it to exponential form once I have no number in front of the log or no negative. Again, this is base 10. To switch it to its exponential form, it's going to be the base to the exponent negative 8.8, and that's going to be equal to this hydronium ion concentration. So it's the base 10 to the negative 8.8. If you put 10 to the negative 8.8 in your calculator, because we're not done yet, notice that the way that we write our concentration is we write it in scientific notation as some number to one decimal place times some power of 10. We're going to have to rewrite what that is. All you have to do is put 10 to the negative 8.8 in a calculator, and you're going to get some approximation. I'm going to write exactly what shows up on my calculator when I do this. It's going to be pretty long. Again, it's an approximation. I have 1.58489.3. How far do I want to go with this? 192. I'll do the whole thing. And then there's that E minus 9. So this whole number portion has to be rounded to one decimal place. 1.6. This E stands for times 10. And the negative 9 is your exponent. Okay, and so that's it on this section.